Hello again, everyone. We are back here with a little lecture on cardinality. So this is essentially talking about the size of sets, which turns out to be an interesting topic in the study of analysis. So in order to discuss cardinality, we first need to recall some basics about functions, particularly notions of injections, surjections, and bijections. So one thing I'll very quickly recall at the beginning is, let's say I have some function, call it f, that goes from s to t. And so if I have say some little s inside of the set s, and I apply f to it, I get, well, this f of s, okay? And maybe it's equal to something, right? I don't know, let's call it t, right? So t is some element of capital T. So in this case, right, we often would say that little t is the image, or if we need to be specific, right, we're talking about this function, the f image of s. And, well, we could also go backward, and we could say that s is, well, let me leave this blank for a second. We would actually call s a pre-image. Okay, so if we're going backward, we'll call a pre-image or an f pre-image of t. The difference here, why I have this little emptiness, is there may be more than one pre-image of a given element t. And so here I actually have to use the word a, right? So the indefinite article. From a pictorial point of view, right? If you have s to t, and I have some little s that gets mapped to some little t via f, it could be that I have some other element, maybe s prime, which also maps over to t via f. And so in that case, both s and s prime would be f preimages of little t. Okay? Now there's a little bit of a ambiguity in this terminology, because we could also ask for the preimage, or the f preimage of t. So if I write the f preimage of t, what I mean then is the entire set of preimages, using this meaning of preimage. Okay, so the f preimage of t is the set containing all elements in S such that f of s equals little t. All right, so usually the context helps you decide whether you're referring to the set of preimages or an element which is a preimage. Okay, so let's get to our main definition here at the beginning, which is, well, again, we'll have the same setup, so we'll let S and T be sets, and F a function from S to T. All right, so the first is that we call F injective. Okay, and you may have heard actually the phrase one-to-one, but I will not use that. So we're going to call F injective if every element of the codomain T has at most one f preimage. Okay, so this picture up here, not injective, because here I have an element T that has, well, at least two preimages. Now it could be I have another element U and there's no arrow going into it. That's okay. This has no preimages. That's fine. Injectivity just says you can have at most one preimage. All right. The second definition, well, we're going to call F surjective. And again, you might have heard onto, which I might say more often. I won't say one-to-one, but I might say onto, but surjective is the official term here. If every element of T has at least one f preimage. So this picture up here, we have no arrow going into U. So it is not surjective. Okay, so for injective, we can only have at most one arrow going into each point in the codomain. And for surjective, we have to have at least one preimage. All right, we have to have at least one arrow going in to each element in the domain, codomain. Okay, and then finally, we're going to call f bijective if every element, oh, we said if every element, if every element of T has, well, this is the intersection of the two ideas, if it has exactly one f preimage. So injective says you have at most one, surjective says you have at least one. Right there in the middle is when you have exactly one preimage for every element, then we call it bijective. So bijective, okay, this is equivalent to saying F is injective and surjective. Okay, and in terms of how we usually prove it, right, usually you'll break it up and you'll say, prove it's injective, prove it's surjective. Hey, cool, now we know that it's surjective. So let's try looking at a couple of examples. So let's say I look at the sine function. So the sine function, I can take any real number, and I get some number between -1 and 1. And this is a surjective function. All right, if we graph the sine function, we know it goes between -1 and 1. Right? Of course, I can go the other way here, right? But the important thing is every value between -1 and 1, I have a preimage. All right, so this down here on the x-axis would be a preimage for, say, this point on the y-axis. Okay, so I have a surjective function when I talk about the sine function. However, it's not injective. So it is not injective. Why? Well, just head on over a little bit further. Again, x prime, you see I have two different inputs that give me the same output. That is, this y has at least two different preimages. Actually, it has an infinite number of preimages, right? That's way more than at most one. Okay. We could fix this injectivity problem, though. So something you might do, and here I'll use a capital S just so you can see a different name for the function. What if instead of taking all real number inputs, I restricted my domain to just being between -π/2 and π/2? So it's the same rule as a function, but I restrict the domain. In this case, if I go here, so this is, say, -π/2, and over here this is π/2. So I'm restricting myself to just this domain. You can see I never repeat a y value. I go from -1 up to 1, and there's no repetitions. Okay, so this would be a surjective, right? I still get everything between -1 and 1, and injective map. And because I have both of them, this would now be bijective. So this is a common thing we're going to do. We start with some function which we know is surjective, it's not injective. We restrict the domain until it is injective. All right, let's do another example. So let's say I have a function g, which is going to take a positive integer and return a positive integer. And what's it going to do? Well, if I take some, say, positive integer n, g is just going to double it. Okay? So if I put in 5, it spits out 10, right? So g of 5 is equal to 2 times 5 equals 10. Okay? All right, so think about this. Is this an injective map? Is this a surjective map? Well, the injectivity is pretty easy to see. If I take two different numbers and double them, I get two different numbers, right? So if I take g of n, I get 2n. If I take g of m, I get 2m. Could these be equal to each other? Right? Could 2n equal 2m? Well, sure, but only divide by 2 here, only if n is equal to m. So the only way that you're going to get a preimage for the number 2n is by taking n, right? So for example, if I know that 2 times 5 is 10, so 5 is a preimage of 10, is there any other number that when you double it gives you 10? And the answer is no. So G is injective. Okay, is it surjective? Well, to be surjective, every positive integer has to have a preimage. Well, what do you double to get 7? Well, you could double 7 halves, but 7 halves isn't an integer, so we can't use that. So in fact, yeah, there is no positive integer that you can double and get 7. So 7 has no preimage, and therefore G is not surjective. Right? In fact, 7 wasn't terribly unique, right? No odd number has a preimage, right? So since no odd integer has a G preimage. Okay, so here's a function now which is injective but is not surjective. Well, before we restricted the domain in order to get a new function which was both injective and surjective. Changing the domain here isn't going to help because it's like we don't have enough preimages to begin with, right? We certainly don't want to restrict that domain any further. But what we could do is restrict the codomain. So if we write down a separate function, I'll call it capital G, the domain is still the positive integers, but the codomain now is going to be the positive even integers. Okay, so I denote that by just writing a 2 in front because every even integer looks like 2 times something. Okay, so these are positive even integers. So this function is the same in terms of a rule. Okay, it just doubles the input. But now you only get positive even integers in the codomain. And in fact, every one of these numbers, right, everything in here looks like some 2n, and so it will have a preimage. So G is both injective and surjective. Of course, this means bijective. Okay, so there's a good couple of examples. I'm going to write down a theorem that we're going to likely want to be using throughout this course. I'm not going to prove it here. I'll leave that for an exercise. But if we have a bijection, turns out we can always build an inverse function. Okay, so bijections are invertible. So in words, if f is some function from s to t, and if f is a bijection, then there exists an inverse function. So let's make that explicit. So there exists a bijection, G, that goes from t to s. Okay, so pictorially, right, we have s going to t via f. Now we're going to get a function which goes in the opposite direction, from t back to s. Not only do we get that, but such that if I compose G with f, so meaning I apply f and then I apply G, it's like I did nothing at all. I get the identity map on the set S. Okay, so if I put in some element from S into F and then into G, I get back that exact same element from S. And if I go the other way, first apply the G starting from T and then apply the S, applying F, I get back to T and it should be the exact same element I started with. So the composition should equal the identity. Okay, and so in this case, we call G, well, it could be an inverse, but in fact, there's only one of them. So we'll make this the definite article, the inverse of f, and write that G equals f, and we use an exponent of -1. Okay, and we just read it as f inverse. Okay, so that's how we'll say that out loud. Okay, so it turns out actually the converse is true if you know that your function has an inverse, meaning it's invertible, then your function must be a bijection. Okay, so we actually, it would go both ways. All right, but now that we have this behind us, we can get on to our main definition for this topic, right, which is going to be for cardinality. So, two sets. So I have two sets, maybe they're S and T, whatever. We're going to say two sets have the same cardinality. Okay, so what does that mean to say that two sets have the same cardinality? We're going to say it if there is a bijection between them. So if there is a bijection between them. And you might say, well, does it matter which order? And the previous theorem says no. If I have a bijection from S to T, then there will exist a bijection from T to S. So it doesn't matter which direction I find this bijection. Okay? Now, if there is a bijection between a set, let's call it S now, and the set, let's write down the positive integers between 1 and n. And I'll often abbreviate this set by just writing n underline. Okay, so here where n is some positive integer. Then we say that S is a finite set. Okay, so if you can build a bijection with a set with 12 elements, you are a finite set. And in this case, we're going to say with cardinality n. Okay, so for finite sets, the cardinality just counts how many elements are in your set. Okay, so in this case, we write, so if I want to talk about the cardinality of the set S, I'm going to use absolute value bars, okay, which again, it's sort of a measure of how close something is to 0, right? The distance from 0. Well, in this case, it'd be the distance from having 0 elements. And so I'll write it looks like absolute value of S equals n. Usually I would say that the cardinality of S is equal to n. Okay. Now, of course, it could be that you cannot find a bijection between your set S and any such finite set 1 through n, in which case we're going to call S an infinite set. So if S is not a finite set, then we will call S an infinite set. Okay, so in some ways that feels kind of bad. Like, what does it mean to be infinite? Well, not finite. But all right, that's the way we're going to do it here. Now, a reasonable question, which, well, actually, it may seem unreasonable, right? You might say, well, okay, if a set has n elements, then it can't have more than n elements. But actually, we're going to prove this, right? We're going to prove that once you've determined that a set has cardinality n, it can't have any other cardinality. Okay, so here we go. So our theorem, which we're going to label as finite sets, have unique cardinality. Okay, so finite sets have a unique cardinality. So as an explicit statement, so if S is a finite set, with cardinality M and with cardinality N, which sounds weird because, well, can't exist unless the conclusion of this is true, which is if you have both cardinality M and cardinality N, then M equals N. Okay, this is one of those things. You're just like, really? You have to prove that? Okay, but we'll do it. So we know that S has cardinality M, and we know that it has cardinality N. And so by our definition of has cardinality N, we know there exists two bijections. So there exist bijections. So say F going from S to the set from 1 to M. So you remember that was our notation up here. If I use a letter underline, I mean the set containing the numbers 1 through that number. So here I have a bijection from S to M, and I also get a bijection, let's call it G, from S to N. Okay, again, this means the set of numbers 1 through N. Okay, but by the theorem we had above, we know that bijections are invertible. So once I get this function G going from S to N, I also get a function going backward, even a bijection going backward, from N to S. Okay, so now I have this bijection. But now we can look at the composition, F composed with G inverse. So this is a function that, well, let's see, G inverse starts with N. So I start with N, then it goes to S, and then S takes you to M. So in total, I get a function from the set with N elements to the set with M elements. Okay, but these are both bijections, F and G. And so their composition is a bijection. Well, F and G inverse even, right? So G inverse is a bijection because G is a bijection. So F composed G inverse is a bijection. So I have a bijection from N to M. This is a set with N elements to a set with M elements. Okay, now let's consider the M elements in this set. Because we have a bijection, we know that each element has a unique preimage. So each element of M has a unique F composed G inverse preimage, meaning there's a unique number in the set N which maps to that M. Okay, since there are M elements and each element has a unique preimage, that means that we are getting M preimages. Okay, thus we have M preimages, okay, or F composed G inverse preimages. But we also know that F composed G inverse is a function. So you can't have one element in N mapping to two different elements in M. So these are M, not just M preimages, but M distinct preimages. Okay, so we end up having M different elements inside of N, right, which are preimages for our elements. Okay, but F composed G inverse is a function. It has to send everything in N to something, which means that everything in N is a preimage. Okay, so as every element in N is a preimage, there are N distinct preimages. Well, how can that be? How can you have both M distinct preimages and N distinct preimages? Well, it can only happen if M is equal to N. Okay, so there's our proof. All right, now this is just the beginning of cardinality. We really want to get into what happens when you move to infinite sets. And so we're going to have another video where we discuss countably and even uncountably infinite sets. We'll see you there.